problem. I draw the beam that was fixed to the wall and I put it on two bars. Let's say this one has A1, B1, L1. This one is A2, B2, L2. Each one has a different leg, cross-sectional area, and material property. And they are fixed at the end of this beam that has length L, E, and cross-sectional moment of inertia Y. And then we apply a force, and we want to see how much the total configuration will deflect at this point. This is an extremely practical problem, and the trick here, we can use the different kind of methods to find the deflection at that point. The trick here we introduce is the method of combined springs or locked elements. And this method in general is very, it has application in various areas of engineering. Now here, we said let's consider this beam as kind of like a spring, right? You see that, you can apply force here and release it, it's going to come back. So that beam going down at that point acts like a spring. So if I model this beam with just a spring at this particular point, let's put it here, like a spring. So this is the spring constant of beam. And then if I model this bar, this little bar here, A2, E2, and 2, with another spring, I call it A2. And if I model the other bar with another spring, I call it A1. So in fact, I have three springs that are connected together, end to end. This connection is called serial connection, because all the ends are connected together. They are in series, right? And if I apply this force at the end of this spring set, then I will get, if I can replace all this spring with just one, then I will get the same effect of deflection that this complicated configuration will give me, right? So that's the objective behind the spring analysis, that I want to simplify a bunch of spring, as you can see here. Here are two springs. I want to combine them into one spring. That's the reason we say method of combined spring. Because you can reduce a complicated structure into a simple structure that you can analyze, right? So before we actually go to that problem, we want to see that solve this problem using the actual deflection. Say deflection here is a combination of deflection coming from this plastic bar plus deflection and this plastic bar plus deflection at the end of the beam. If you do that, then you can find the deflection. That's one method you did, and find the spring constant of equivalent spring constant. Right now, I don't want to consider this particular problem, right? I don't want to limit myself to this particular problem. So I go back to the general spring. Let's say this spring could be anything. It could be beam, bars, torsional shafts, anything, right? So I'm trying to find, let's say I have two springs, K1 and K2. I'm trying to replace these two springs connected in series with just one spring that has the same effect of displacement, the same rigidity, right? So what would be the expression for the replacement spring in terms of the spring constant of K1 and K2? Well, in order to find that, I say that deflection, assuming that this guy, right, has deflection. Let's call it delta X total. So if you apply force here, that's going to deflect amount with, say, delta X total. Right? For the biggest spring, you can write F is equal to, the force at the end is equal to K total delta X total. Right? So what can I write for delta X total? Delta X total here Yeah,
Just
in
some of
each
it.
one of these springs, right, from here to here, you for this one you have delta x2, for this one you have delta x1, right? So delta x1 is equal to what? Is the force in the spring, which is F, the same F, divided by K1. Right? What about delta x2? Delta x2 is equal to the force in the spring again, because they are connected in series, it's the same force. Divided by K2. Right? But here, what do I have for delta x total? Let's write this equation. This is for the other spring, the total spring. If you divide this by K total, you get F over K total is equal to delta x total. The total delta x, the total deflection. What is the total deflection? Combination of delta x1 plus delta x2 is the total deflection for the replacement spring. So instead of delta x total here, if you divide by K total, you get delta x total. You write delta x1 plus delta x2. What is delta x1? F1 over K1 plus delta x2, F2, which is F. These are all F, the same force, over K, Q. Right? So from this equation, divide by F, then you get 1 over K total is equal to 1 over K1 plus 1 over K2. So if you have two springs, when I say spring, I'm not talking about actual spring, as you know that. If you have a bar, beam, shaft, anything, any structural component that behaves like elastic, linear elastic material, right? You can replace this series connection with just one spring, that 1 over K total is equal to 1 over K1 plus 1 over K2, right? Now, let's go to another configuration. Let's say I have two strings, A1, they are connected in parallel, A2. And let's say this connection only can move in the x direction, not moving in the y direction. There you go. So we put some constraint here that this configuration can only move in the x, so you don't have, they move the same amount. That means that they both move the same amount. So let's put the F here. Force at the end. Let's use another color here. Color use green. Let's put the force color green. F. F. Now, my objective is, if I want to replace K1 and K2, that configuration, with just one spring that is going to mimic the effect of two, then what should I write for the spring constant of the replacement, the total of the spring? That means if I lump these elements together, these two springs, and just put one K total. What would be the expression for K total in terms of K1 and K2? How can you prove it?
Because the x, K1, K2,
So let's write it in this way. So if you have floating force, you know that they have the same amount of deflection, both of them, right? So if you write delta x for that, what would be the delta x for this? Delta x1 is equal to the same delta x is equal to force in this member, let's call it F1, divided by K1, right? And delta x here, delta x2 is equal to the same thing, delta x2 is all the same, right? It's equal to the force here, F2 divided by K2. But look, F1 and F2 are not equal to F. You see that their summation is equal to F. Because when you apply force here, it's going to be shared between these two guys. You see that they're not, F1 is not equal to F2 necessarily, it's not equal to F. Take this as a system, write free body diagram. What do you have? You have an F here on the right, right? The forcing is spring 1, the forcing is spring 2. Right? That's the FPD4 is plate, is rigid plate. That plate is rigid. So what do I get here? Summation of force in X0 is in equilibrium, right? Then you have F is equal to F1 plus F2. So just use this equation. Let's write that equation. F is force is equal to F1 plus F2. The distribution of the total force to each spring. So what can I write for F1? Delta X K1 plus, what about F2? Delta X K2. So far I can factor out this delta X and I get K1 plus K2 times delta X. But what can I write for the F total? The same delta X, because look, we're trying to replace this configuration with a spring that is going to mimic that. So it's going to have the same delta X with the given force. That's the reason we have this force here. Method of combined or lumped elements. That means that they're going to mimic the original system exactly. So that means instead of F, I can write K total times delta X, the same delta X that I have here. And also I already have this equal to K1 plus K2 delta X. So now you can cancel out delta X and then you K total is equal to K1 plus K2. Okay, so let's make a summary. Now if I have three elements here, what do I get? 1 over K total is 1 over K1 plus 1 over K2 plus 1 over K3. So it doesn't matter how many elements you have in connection in series. What about this guy?
K1 plus K2 plus K3.
Just summation of. So now let's consider one more example of, before we actually go to the structure analysis question, like the one I had before. Let's say you have K1, K2, K3, right? Now, let's say each one of these is 1. Let's say this is 1, 2, not 1, 2, 3, 4. Now you want to replace this entire thing with the 1 equal K total string that when you apply force F here at the end, it's going to behave exactly the same. There you go. Say it again?
Here's how you do it. You must use a formula.
Yeah. So what should I do if I want to replace or simplify this into one combined, one total spring?
K1 and K2.
Yeah. So first start with these two guys, right? These two are in parallel. So what should I do?
Yeah.
Um,
K1 plus K2.
K1 plus K2, right? So here, you put, all you do is say these guys, I just combine them together. According to the formula, if they are in parallel, you just put K1 plus K2. So I put one spring K1 plus K2, which is equal to 1 plus 2, 3. Right? And there is another spring, 3 here. And there is another one, 4 here. So what is the next step? This spring with this spring is in series. So 1 over the entire thing, 3, plus 1 over 3 is equal to 1 over K total 1. So if I replace that with K total 1. So that's the formula I get for K total 1. So this becomes 2 thirds. So K total, don't forget to invert it, is equal to 3 over 2, which is 1.5. So the next step, I put one spring here, 1.5. This is in parallel with 4. So what would be the next step? 2 springs are in parallel. What should I do? Add them together. So the final thing is K total is equal to 1.4. 1.5 plus 4 is equal to 5.5. There you go. That means if I apply a force F at the end of this guy, right, then the deflection, because our objective right now in this chapter is to find deflection. The deflection is equal to force divided by K total. The total is spring constant. And what's K total? 5.5. So the force at the end of this is equal to 5.5 times deflection for this configuration. Now you may wonder, well, what is the purpose of this if I want to do a structural analysis? Well, you can just simply combine this into a lot of problems that we solve in this class. For example, let's say we have a beam that is supported by 2 columns. So the first column is just simply a straight bar. The second support, you have this straight bar, right? But it's mounted over another beam. And this beam is also mounted to 2 bars with different cross-sectional area. Now the question is, if you apply force 2K here, how much this is going to go down? Obviously it's going to go down like this, right? Find that delta. Now imagine Imagine, if you want to solve this without using a spring constant theory, without using combined spring, it's very hard. Right? So what should I do? Now let's put some numbers here. Let's say from here to here is 4 meter and EI is 1. Okay? And for this, also EI is equal to 1 for this beam. And the length is 1 meter. And for this guy, L is equal to 0.5, and A is equal to 1, E is equal to 1 for all of this. And the length is also for this guy is 1 meter. Right? Some numbers. So therefore, the length here approximately also for this is 1 meter. 1 meter. So 1 plus 1, this 1.5, plus, let's say this is also half. So this is 2. From here to here is 2. A is equal to 1, A is equal to 1. So this is all the data we did. In practice, well, this is made of, for example, steel. Fe is 200 gigapascal. A is a small. Alright? But here we just take typical values, 1 unit. Right? Just able to solve. So what should I do? Well, I need some spring constant for this beam. Right? So if you go to a table, if you go to, for example, you can use double integration, you can do this. In fact, let me use double integration to get it. I don't want to go to table. So let's say you have a beam. This length is L, and E and I is constant, conjugate of elasticity, area moment of inertia, and the length is L. And then you have a force P here at the middle. P. Then I want to see how much this point is going to go down. Delta, right? See? It's going to go down like that. You have a slope here and another slope here, right? So what should I do? If I want to do double integration, I have EI, V double dot is equal to mx. This is the deflection of neutral axis or elastic line. Have you started your homework? I posted last time. Start because the deadline is next week. Next week the same day, Thursday, and it may take some time to figure out. Right? So you have solved this equation. So all I need is the moment. So if I do that, and it's become F really, this is P over 2. P over 2. P and everybody. Mx from the left. And then I write moment at that point. Plus P times every side x minus L over 2. Minus P over 2. X is equal to 0. That means mx is equal to P over 2, x minus every side, x minus L over 2. Again, as you can see, this P is going to be distributed to half. So you can emit from symmetry. You see, I didn't write summation of force in y0, summation of moment. When you have P in symmetric at the middle, then it's L over 2 from here to here. And this is P over 2, P over 2. Right? Then I write moment equation at this point. We get mx plus P times this descent, which is x minus L over 2. Minus P over 2 times x is equal to 0. So you get, take everything to the right, P over 2, x minus m squared, x minus L over 3. So put it here. Then you have EI, V double dot is equal to E over 2, x minus m squared, x minus L over 2. Integrate, first integral is equal to E over 2, x2 over 2 minus x minus L over 2 over 2 plus C1. Can I find C1 here? Yeah.
Shouldn't it be 2 times heavy side x minus L over 2?
Yeah, if I take out this P over 2, then because this is P over 2 and this is P, right? If I take it to the right and factor out P over 2, then this becomes X, which is fine. So this is fine. But if I multiply that by this, there should be a 2 here. Thank you. There should be a 2 here. So when you multiply that, these 2 cancel out with these 2, so you get negative P x minus 2. That's right. So here, when you put it there, you have EI, V double dot is equal to P2 x minus 2. There is a 2 here. And when you integrate EI, V dot P over 2, x2 over 2 minus x minus L over 2 to the second power. So if you take derivative of that, that's going to give you this one, plus C1. Now the question is, can I find C1? Right now. No. Why?
You don't have the source.
Because I don't have a condition on it. Right? If this was welded to the wall, you know that this slope would be like this for weld. Right? So the slope here is 0. So the slope is just what? V dot. So you could say, for example, at x0, V dot is 0, so C1 is 0. But unfortunately, I don't have information for the slope right now. So what do? Integrate again, so you get another C2. Then you can apply conditions. What are the conditions? X is equal to 0 at 0. X is equal to 0 at M. X at L. V is equal to 0. So V at x0 here is equal to 0. V for deflection at xL is equal to 0. These are 2 conditions that I have. I don't have anything for V dot. So here I can only impose it to get C1. So go ahead and do one more integration. So EI times V of x, I don't write x here anymore, is equal to P over 2 x3 6 minus x minus L over 2 3 over 3 plus C1 x plus C2. Now I can apply boundary conditions here. So what is the deflection at x0? So this is 0, 0, 0, 0. So C2 is equal to 0. Now this condition, deflection at x, this one, is equal to L, should be 0. Now put it here. You get 0 is equal to P over 2 L 2 over 6 minus L minus L over 2, which is L over 2 to the third power over 3 plus C1L, and C2 is already 0 is equal to 0. To solve that for C1, then you get, so this guy becomes 1, 6 minus, this is 8, 24, right? So here, if you do simplify 24 and 4, 24, so it's 3 over 24. So it's 1, 8. So this guy is 1/8 L cubed. So you get 0 is equal to P over 2 L cubed over 8 plus one is equal to negative PL squared over 16. So PL squared 16 with a negative sign. So the equation of elastic curve that I asked in the homework is going to be EI V at any x, put it here, is equal to P over 2 x cubed over 6 minus every side x minus L over 2 cube over 3 plus C1, which is negative PL squared over 16 times x, and C2 is also 0. So that's your equation. Now, this gives you the deflection at any x, right?
What happens to the other L? In your equation, I'm sure that you circled where you put the L's in the spots.
Which one are you talking about?
Yeah.
This one?
Yeah, you have heavy side X minus L over 2. Shouldn't it be L minus L over 2? When you plug it in?
Show me exactly what it is. You're talking about this guy?
Yeah.
So yeah, when you put L minus L over 2 is L over 2.
Okay.
There you go. Yeah, it is possible that I'll do this calculation, so it's good that I always verify what I'm doing here. So you get this equation for equation of elastic line, right? So this gives you the deflection any point across this beam. Look, we're not solving this problem yet. This problem is more complicated. We just consider one beam that is supported at two ends and supported at the middle. Like this one, like this one. You see that? So I'm trying to find the deflection at the middle. Why? Why I'm trying to find the deflection at the middle in terms of force? The relation between force and deflection at the middle. Why? So you get a relation for a spring constant, a formula for a spring constant. You can get it from the book. Go to the first page, as we explained last class. You go to the first page, and there are a lot of formula there. But I just wanted to do double integration just to practice, right? Because we have enough practice for double integration. So now here, what I need to find deflection at x is equal to L over 2. What should I do? Just plug in L over 2. I can easily see that some people even don't know what's going on here. I can see that. And the thing is, usually these are the same students that when at the end when they get F, they come to me and say, can I get a C to pass? No. You had 1 full semester, like entire classes, you could ask questions, you could say, why do we get that? Just stop me, don't let me go. So evaluate this at L, x is equal to L over 2. What do you get? So you get EI, let's write some space. EI, the deflection is equal to P over 2, P over 2 times L over 2, cube over 6 minus, this is 0, right? Minus PL square over 16 times L over 2. So what do you get? Simplify that, so you get, this is 8, 1 over 2 times 6 times 8, P L cube minus P L cube over 2 times 16. That's your EI. V at x is equal to L over 2. So what do you get? something for a bottom that can handle both of them. So this is 32, this is 96. So what should I put here at the bottom that I can add this fraction together? 96 divided by, first one is 1. Right, so PLQ, 96 divided by 32, minus 3 PLQ. So you get what? Negative 2 PLQ over 96, or negative PLQ over, say that?
48.
48. Two times 48 is what?
96.
96. So that's the equation you get at the middle. That means if you have a beam that this length is n, right, and the modular of velocity E, crossover area of inertia is I, then the deflection, if it's simply mounted into support, then if you have a force P here, the deflection is delta is equal to, use this formula. So you have E I deflection at x is equal to L over 2, which is simply our delta, right? Is equal to negative PLQ over 48. PLQ over 48. So you have that. So let's put it in a table. Let's make a little table here before we actually solve actual problem. This is an actual problem we're solving. So let's make a little table here. So if you have a beam like that, support, length L, E, I, and then you have force here, E at the middle, then delta, this is delta. Then delta is equal to E, what is the formula? Over there. E, LQ, over 48, EI. Negative PLQ 48 EI. Right? Now, what about the bar? What else do I have here? I have a beam and I have a bunch of bars. The rest is the same, right? The rest is the same. Now, if this was fixed to the wall, then I had to find the deflection for a beam that one side is fixed to the wall, right? So for a bar, what do I have? A, E, L. What do I get for the spring constant? For the deflection? If you write sigma is equal to, you guys had mechanics of material before, right? I think you all had mechanics of material. So in mechanics of material, we had sigma is equal to E epsilon for this bar. What is sigma? Force over area, E over A. So we put P here. And the cross section is A. So this is going to be formed like that, right? And this is your delta. So sigma is equal to P over A. Is equal to E is right here times epsilon. What's your rate for epsilon? Delta. You see? The absolute deflection divided by initial length, L. So what do I get for P? P is equal to AE over L, right? Times delta. So let's write it here. So So delta is equal to PL over AE. So I have everything I need in order to solve this problem now. So let's get rid of all these recalculations. So first of all, before I actually go to combine this spring together, what is the spring constant for this beam? So I want the relation K is equal to something. Say that. K is equal to negative 48 pi over L cube. How did I get that? So basically, you say that if I replace this beam at this point, right? The point is also important. What point? If I replace this beam at this point with the spring, right? Okay. That if you have this force P, it's going to have the same amount of deflection. What is that spring constant? You are saying that if I have P is equal to K delta. What is my K? Now, rearrange this formula in this form. 1 by 48 EI divided by L cubed. I'm just rearranging this formula. So you get P is equal to 48 EI over L cubed times delta, just absolute value. So compare this relation with that. What is my K? 48 EI divided by L cubed. You see that? So that's the spring constant. And what is the spring constant for the bar? Is equal to K is equal to AE over L. Now I'm completely ready to replace that with the springs. So what should I do? What should I replace this guy? Let's label that. Let's say this is member number 1, member number 2, member number 3, member number 4, 5, 6, 7, 8. Right? Now convert these guys to the spring. For 7, I put the spring. Like that. So K7. What about 5? In series. K5. You see that? K7, K5, K8. K6. What else? Then these are simply, this point become rigid, right? This point, but that same, we assume that this goes the same amount of deflection. And then you have a K, what member is 4? That is with this series. This K4 is the rigidity of this beam here. And we already have a model for it. Right? Now, what about this guy? K3 in series. Right? And you come to this end. Now, starting with the other side. What should I write here? K, 2 for this entire column. And this one is also rigid. Because we assume that this only goes in Y. You see this roller here? It doesn't deflect like that. If you have a theta like that, this is not valid. We assume that it has exactly the same amount of deflection. Then I add my K1. Now let's do the calculation, and this is my force, P. What's P? 2K. Now let's go to the calculation. What do I do for K1? Which formula should I use? Because in the test, I'm going to give you this table. You don't need to memorize. The one on the top, right? You see, this spring here corresponding to this is just are mounted, and you have a force at the middle. So K1, I should use this formula. So I put 48 times EI, which is 1 divided by L cubed. L is 4 Q. What about K3? The length is half. So which formula should I use? You say this, is it 3? Yeah, this one is 3. So what is this? It's a bar. It's a bar, right? So which formula is it? K3, right here. You see? This one is a bar and mounted on a beam, and this one is also mounted on a bar, and this one is also mounted on another bar. This kind of exploded view. You see? This configuration. So 3 is a bar. So what formula, which one should I use?
3/8.
It's a bar, it's not a beam. You see, this is a beam. It's a beam. It's a bar. So I should use this. So AE, assuming AE is 1, so I get 1 over L. So L is half. So this is going to be 1 over half. Because AE is 1, right? L is half. So 1 over half. Now I go to this beam. What about K4? K4 is equal to, again, 48 EI, which is 1 over L cubed. And L is equal to 1 meter cubed, then K5 is equal to, please pay attention. K5 is equal to this one, K5. So you still use AE over L as K7, 1 over 1, 1 over half, 1 over 1. And now we have everything, and this one is AE 1 over 2. Right? A over L. L is 2 from here to here. So now, what should I do? First, I add this together and this together. Should I add them or 1 over K total? I shouldn't add because they are in series. So 1 over K5, so you do that. 1 over K5 plus 1 over K7 is over 1 over K total, 1. Let's say please replace these two guys with a spring K total, 1, right? So that would give you 1 over K total 1 is equal to, so this is 1 over K5, which is 1 over half, plus 1 over K7, which is 1, so you get, this comes to the top, half plus 1, so it's 1.5. So a spring here, let's replace this with a spring. The spring constant is 1.5. right? Now, replace this guy with another spring. Again, the same thing. You see 1 over half, which is half plus 1 over 1, which is 1 over 5. Look, 1 over K total is 1.5. So what is K total? 2 there. You see 1 over K total? Nobody was paying attention. 1 over K total is 1.5, which is 3 over 2. So what is K total? 2 there. Don't forget to invert it. So the spring constant here is 2 there. This one is also 2 there. So what is my next step? 2 springs are in parallel. What should I do? Add them. So 2 there plus 2 there, 4 over 3. So you're gonna get, let's write it here, you're gonna get the system line 1 over half and 48 over 1 cube, which is 1. Then summation of that is equal to 4 over 3. Right? So what should I do? 1 over this one, which is 1 over half, plus the inverse of this one, 1 over 48, plus 3 over 4 is equal to 1 K total is equal to, so that's going to be half plus 148 plus 3 over 4. Now, you know what? Let's see the calculator, man.
It's 1 cube.
Each one is 1 cube. It's one. The reason that I keep 1 cube here, so you can go, when you go home, you can decode it and say, well, there was an L cube coming from this formula, and the length was 1, so 1 to the third power. So that's going to be we're going to have another new calculator soon after this. Half plus 1 over 48 plus 3 over 4. 127. And then you inverse it. Then 1 divided by answer is 0.8 total is equal to 0.787. Okay? So the entire left side is what? We can replace it with a string that K is equal to 0.787. So what should I do next? Add these two, because these are in parallel. So half plus that, so 0.787 plus half. Then you get the entire thing, this entire bottom is going to be, the spring constant is going to be 1.287. Now what should I do? 1 over 1.287 plus 1 over this guy, which is 4 cubed divided by 48 is equal to 1 over K total. Then you find K total. Now if you find K total, what can you write about deflection at this point? What can you write about deflection at this point, delta? Delta deflection is equal to? P, what is P? 2K, right? 2K divided by K total, whatever it comes. And what is K total? It comes from series addition of this big spring to that. You see? So this problem is probably the most complicated. You know, they use software to do that. But you can use method of combined spring to quickly calculate it. Right? And let's say you use a software, you go to the software, you model it, what should you get from software? The same thing, 3 significant digits. As long as the deflection is small, very small. But what's the assumption for this relation? What's the assumption for this relation? A small deflection. So when we had method of double integration, the basic assumption was the deflection is small. But now in the software, if you increase this 2K, make it 200K, what happens? You get larger deflection. And still, your theory, the value that you compute from this formula, is going to be close. But you eventually get deviations. Now, continue adding more force. Let's say 2000K. What do you get? It may break, but you may get a very large deflection. Now you reach to a region that even software is not predicting well. So what should you do? What's the verdict? What should you do? The ultimate answer is you go and build a sample in the lab. That's the most accurate measurement. Even the software, don't take the software at granted, but this software is the best thing ever. Whatever it gives me, I'll just use it in the work. The software will solve a bunch of equations that are similar to that, but more comprehensive. So the software will get a better approximation that you get for your equation, but not for any number. Yeah.
Is there a quantitative limit on deflection that we can use the double zero method with? Like, is there a number that's less accurate after?
You can drive that number. You can. In fact, I can define that as like a meter vapor. If you know how you drive this relation. You know how to drive this relation. Ui, second derivative of b is equal to mx. The derivation of this is given in mechanics of material, of course. Then you take an element, let's say this is beam, you remember? Then you take an element, let's say radius of curvature. Then you take an element here, and with the deflection theta, and this radius of curvature, then you can use that equation. And then, here there was some other terms here. There was some square root of 1 plus dv dx to the 3 over 2. Some nonlinear term. And he says since dv dx is 0, the small, then this value is small, so you get rid of this almost becomes like unity. But now, in order to get that error, you have to go back and model that term that you brought, the bound. How much is that bound? So that depends on the type of the beam, cross-sectional area, the location on the beam, or the location on the beam. So it's not a simple formula, it's a complicated formula, yeah. Any question?
The blue K total equals 0.787, what is that summing up?
That comes from here. That comes from.
That's summing up that whole top part?
No, this is summing up all this bottom together. Not this one. It's not the K. This is not the K, the real total, because we use 2K to find the deflection.
All of that top green part plus.
No, it's gonna be
It's just the bottom.
this plus this plus this, all these things plus the right part. These two columns. Yes. Left part, right support. Two support. So, hold on. That is this one. That is this one. I forgot it myself. That is for this side.
Which is your numbers up there in the green, right at the top?
Which one is it? In the green?
The 0.5 plus 1 over 48 plus 3/4, that's that whole bottom left side.
So this becomes
1.27.
1.27, but look, this is 1 over K total. You have to inverse it to get the K total. So do 1 over 27, and then you get 787. No, I did not. I said 1 over K total is 1 over this, 1 over this. Do that one more time, and then you can verify. So now, final thing, I want to add something to this table, a torsion. For torsion, you put a T with a torque T, then you have a deflection T. So what was the spring constant for torsion? You have a shaft. This is the polar moment of inertia. Is equal to J. And then I apply torque. Torque T there. And I want to see, and let's say this is length L. And this one end is fixed to the wall. Right? And I want to see how much this angle is in terms of the length and shear module of elasticity and everything else. So what was the relation for torsion? Do you remember that? You had T equal to torsion. Is equal to Tom X R over R, and Q, and including that R over R, K, which is R, PR, just put K, F times R over the area, then you get T, torque. Torque is equal to Tom X, R squared, which is J, over R. So Tom X is equal to PR over J. Put it here, Tom is equal to PR over J. R over R, cancel out with PR over J. And phi is G at the surface, G times delta, which is R P over L is equal to PR over J. R cancel out with R, then you get torque is equal to GJ over L T. So this relation was GJ over L P is equal to torque. Assuming you already have this piece of material. So for torsion, we have this relation. Because I'm going to give all these formulas to you. You don't need to memorize. So this formula is given. DJ over L. Okay. So what's the spring constant? Let's say you have shaft like that with length L, shear module of elasticity T, and you actually apply torque like that. You twist it. When you release it, what happens? It's going to come back. So this is going to act like a portion of the spring. So what's the spring constant? Is equal to, you go here, you say torque versus deflection. Torque is like analogous to force. If the angular deflection is analogous to the strain. So this is your strain constant, K. Now question, a meter measure. So this, let's say this L3, G3, J3, L2, G2, J2, L1, G1, J1. Now, let's say apply the torque T is equal to 2 kilonewton meter at this end. Then find the angle of deflection. Find angle of twist. So at this end, when you apply the torque, let's say this is the original line, right? When you apply the torque at this end, this line is going to rotate the speed. Find that speed. Yeah. You want to do that?
I think I have something, but
Yeah.
I mean,
You can do it. Something. Okay, what? You can do it. Yeah. Can you go to the on the other side. That's EJ over L. Yeah, but that's okay. But if I want to use the method of, you see what he's doing, replace that with one spring. Now, how many springs do you have right now?
3.
3. How can you replace with just one spring?
Actually, some of the
Now you have got to figure it out. What is the connection? Is it in series or parallel? Yeah, so go ahead. You go ahead and play. So when we had the spring in series, what did you do to find the spring constant of the total? 1 over K total, yeah, is 1 over K1, which is L1 over Q1, J1, yeah. So you can write it like this. You can write it like that. Yes, say it's getting to the point.
So that would be 2.
Mm-hmm.
We
Whatever that
we
formula
need
is.
values plugging in.
Yeah,
And
That's
then
right.
compute the inverse of that.
that's right. That's it. So, I think we already had 100. What were we trying to do? But email me, both accepted. You know, the way he did it, he said he used superposition. He said find the free total is P1 plus P2 plus P3. But look, if you have in the case that you have two shaft in parallel. You see? Let's say you have this one, and then this one, and they connected to a plate, and you are going both here. Right? They're in parallel. In this case, this approach is not very intuitive. So we use the spring constant here. So 1 over K total is 1 over K1, which is reverse of that relation, which is L1, K1, J1. Then all you do, because do this, which is the bigger formula, reverse it, and then put it here, and it's 50K. So you find negative 50K.